233, 12, 33.
Man is a mobile creature. Ever since his earliest days, he's moved from one place to another, exploring the world around him. And always his movements have been guided by maps. In the early days, maps were very crude, but what they lacked in accuracy, they made up in artistic decoration. Always there was the effort to improve the map-making process, to update maps and make them more useful. The more accurate the map, the easier it is for a traveler to reach his destination. For a construction engineer to plan a project. For a nation to establish its boundaries. Even for an Earthman to venture into space. Nowhere are maps more important than in the military. They define areas to be occupied or defended. They may illustrate natural features of those areas, hills and valleys, rivers and streams, forests and clearings. They may position man-made additions to the landscape, villages and cities, trails and roads, railways, airports, bridges, any man-made project of significance. The military man depends on his maps for knowledge of the terrain where he will be operating. Small-scale maps tell him about overall regions. Medium-scale maps give him more detail about an area within a region. Large-scale maps give him even greater detail in a more confined area. They show terrain features and elevations clearly and often indicate specific buildings and structures. Maps can be topographic, showing horizontal positions and vertical elevations. Or they can be planimetric with only horizontal position of features. They can be photo maps, or plastic relief maps, or special purpose maps. Regardless of scales or type, all maps position the areas shown with relationship to an imaginary grid system that men have established on the Earth, a means for identifying the location of any point on the Earth's surface. The lines are designed as longitude and latitude. An understanding of this system is basic to map making. The Earth rotates around an imaginary line called its axis. The axis intersects the surface of the Earth at the north and south poles. Any plane that contains the center of the Earth creates an arc on the Earth's surface, known as a great circle. A plane that includes the Earth's axis creates a great circle arc known as a meridian. There are an infinite number of meridians, all passing through the north and south poles. The meridian that passes through the Royal Observatory at Greenwich, England, is called the prime meridian. The great circle, whose plane is perpendicular to the Earth's axis, is the equator. Degrees of longitude are measured in the plane containing the great circle of the equator. Degrees of latitude are measured in the plane containing the great circle of a meridian. degrees of latitude and longitude are further broken down into minutes and seconds. Thus, a point on the Earth's surface can always be positioned exactly by defining its latitude and longitude. The latitude is given first, followed by the longitude. This spot is located 39 degrees 12 minutes north latitude, 77 degrees 22 minutes west longitude. When a point is thus positioned on the Earth's surface, it is said to be accurately located. The job of the mapmaker is to accurately locate a number of key points in the area he is mapping. There are many points on the Earth's surface that men have already controlled by conventional survey methods. They are marked usually with a concrete monument. These basic monumental control points, called triangulation stations, are often the starting place for controlling other points in the area. When the mapmaker transfers these points and their surrounding features to paper, a map is begun. Traditionally, control points have been established by teams of men traveling through the area to be mapped, using measurement devices to record horizontal distances and vertical elevations. Their calculations were then used by men who actually prepared the maps. Field surveys are still an important part of the mapmaker's job. Aerial photography gives the mapmaker an opportunity to see the entire area he is mapping, to observe the relationship of one feature to another. It has greatly influenced the 4 phases of mapmaking: planning, surveying, compiling, and reproduction. Planning involves the decision to map a certain area. It establishes such things as the scale desired, the amount of detail, the procedures that will be used for acquiring control, an analysis of available information on the area, including existing aerial photography and field survey reports, what new photography is needed, what procedures should be used in compiling the map manuscript, and so forth. If adequate aerial photography is not already available, a photographic mission is ordered. The altitude of the aircraft and the focal length of the camera are determined by the desired scale of the map. The plane makes a number of runs over the area following a carefully planned course. The camera shutter is timed so the resulting pictures will overlap one another. This is very important to the mapmaking process. After the mission, the photos, each 9.5 inches square, are arranged in the order they were taken, and they are carefully analyzed. The mapmaker is looking for identifiable basic control points, and also for prominent features that can provide supplementary controls for the area. Aerial photography can provide the degree of accuracy that is needed for today's mapmaking. The exact position of the aircraft and its precise altitude are never known, so it's impossible to determine an accurate scale. Even if the camera were always perfectly level, only the portion of the picture directly below the lens would be free from displacement. And when the camera is not level, the whole picture has some displacement. So what is required is a means to acquire a positive control. A way to establish the exact latitude and longitude positions of features in the area being mapped. Where possible, this is done in the traditional way, by surveying. If you're an individual who likes the great outdoors, then surveying is the phase of mapmaking you'll enjoy most. For the survey team must penetrate the area being mapped. The surveyor may find himself in dense forest, in parched desert land, in icy Arctic regions. He must be prepared to live out of doors under adverse conditions to get the job done. What he seeks first are the monumented control stations that represent known positions on the Earth's surface. Working from a known position like this, he sets out to relate supplemental control points to it. One way of doing this is a technique called triangulation, usually used in hilly country. Triangulation is based on a single principle of plane geometry. If you know the distance between 2 points, you have a fixed baseline of a triangle. Then all it takes is a measurement of 2 angles to a third point, and you can calculate the length of the other 2 sides and precisely position the third point. Using the 2 sides you've just established as 2 more fixed baselines, other angle measurements can be made to establish 2 more triangles with their third points known or controlled. The whole process just keeps on extending itself. As a check on the accuracy of their measurements, the triangulation process works toward a second known basic control point. The computation of its location should agree with its known position. So the surveyor must begin his work by establishing a known baseline. The second point must be easily visible and should be reasonably accessible. In some areas, towers may have to be built over the point to make it visible. The height of the tower must be carefully calculated because the measurement will be made to its top, yet it is the position of the Earth's surface that must be established on the map. Distance between 2 points can be measured by modern electronic distance measuring equipment. In some cases, it may be measured on the ground by tape. Angles between 3 control points are measured with an instrument called a theodolite. Observations are carefully recorded in the field surveyor's notebook for use by the map compilers back at the base. Identification of each point is especially important. To this point, the surveyor has been establishing only what is known as horizontal control, the position of control points in a flat plane. To determine the elevation of these points, he does what is called leveling. The surveyor starts from a basic control point called a benchmark, where the elevation above mean sea level is known. He sights through a leveled viewer at a measurement rod held on a second point. He can see how much the point is above or below the basic control point. He may also use an altimeter similar to those used aboard aircraft to determine their altitude. He records time and temperature to be sure the reading is absolutely accurate. Triangulation and leveling have traditionally been rugged work, often involving long hikes and difficult climbs in rough country. But today the helicopter has greatly simplified the surveyor's job. It can transport him to and from lofty hilltops in a fraction of the time it would take him to reach them on foot. At night, it can bring him back to camp and a touch of civilization. This time can be profitably spent checking and rechecking the day's measurements. This is extremely important, for they are the basis for all the work that must follow to complete a map of the area. The surveyor may also refer to prints of the aerial photographs, using a pinprick to mark the points he has controlled. He carefully identifies his markings on the back of each photo. A second method of establishing mapping controls is called traversing. This technique is often used in level country. Moving from a known control point, the chainmen use a tape to measure the distance to the next point. Or measures the distance by the use of EDME. The instrument man uses a theodolite to determine the direction the line runs. Sighting is done on a target. The plumb line under his tripod ensures that the vertical axis of the surveying instrument contains the point on the ground. As always, every measurement is carefully recorded in the field notebook. The surveyor can make a complete circuit of an area, establishing mapping controls as he goes, or he may choose to tie into other known control points. An important part of the survey mission is the field classification survey. Its purpose is to identify and classify features that are seen on the aerial photographs or to annotate any changes that may have occurred since the photos were flown. The surveyors record names and other pertinent data on a second set of photos. All the data the surveyor collects is put on two sets of photographs. One set identifies the control points, the other the field classification survey. The control photo contains the pinpricked control points on the picture side and the control data on the reverse side. The photos are then used to complete the next step of the map-making process, compiling. Compiling is essentially the task of transferring the information into a form that can be made into a map. The manuscript is the completed compilation. Grid lines are drawn to the scale the planners had ordered. The basic control points are plotted on the grid using data obtained from the survey team. When the grid is completed, the mapmaker must relate the control points on the manuscript to those same points on the aerial photographs. Then he can begin to fill in the details. To do this one way, the negatives of the aerial photos are fed into a reduction printer, where small photographic transparent positives are made on 54mm by 54mm glass plates for greater stability. Diapositives, they are called. The compiler uses them in a stereo plotting device called a multiplex plotter. The plotting unit consists of a number of vertically mounted projectors. These projectors are used two at a time to project diapositives of overlapping photos onto a mylar base. One is projected in red, the other in blue. The compiler wears special glasses with one red and one blue lens. Thus, the red image is rejected from one eye and the blue from the other. So he sees what the camera cannot show, a three-dimensional or stereo view of the terrain. If all the projectors are used, he has a stereo view of the entire flight line of the camera aircraft. In other words, the multiplex plotter gives the mapmaker a model in space of any segment of the mapping area. He uses it to plot supplementary control points, both horizontal and vertical. This is used to add to the ground survey. It is called multiplex triangulation. In cases where known control points are concentrated at one end of the strip, he can use a technique known as cantilever extension. This extends the control down the strip, but there is no way to check the accuracy of the extended portions. This technique is used to extend horizontal control into unknown areas. A more desirable and accurate type of control is known as bridging. This is used where there are known control points at the end of the strip, and the mapmaker wants to fill in with others. When the control points are established, the terrain features and other details can be filled in. Another device used for compiling is called a high-precision stereo plotter. It uses glass diapositives that are the same size as the aerial negative, and therefore provides images that are more detailed than is possible with the smaller slides used in the multiplex plotter. This equipment has a capability that permits the displacement in slightly tilted photographs to be corrected before the transfer is made to the manuscript. When photogrammetric control is established, the compiler goes to work filling in the details, such as rivers and forests, drainage canals, roads, rail lines, and so forth. A mobile tracing table enables him to relate the stereoscopic model in space with the manuscript. He moves a white dot on the table's surface, tracing a cultural feature. A plotting pencil directly under the dot draws the cultural features on the manuscript. When he's finished, he has a drawing of the mapping area with every feature positioned properly in a flat or horizontal plane. Achieving this stage of the manuscript is called planimetry. To get the terrain features at the proper elevation, the compiler must draw the correct contours. The platen has a small white dot which can be raised or lowered, so the compiler can make any part of the terrain surface appear to be at the same elevation as the dot. What he sees looks something like this. He sets the dot at a specified elevation, locks the tracing table, and begins moving the table, keeping the dot on the ground. As he does this, the plotting pencil traces a contour line representing the same elevation. Then, depending on the contour interval desired, he resets the elevation of the platen. He then locates the dot on the ground, and he traces another contour line. Contouring is not an easy job. Good stereo vision and excellent hand-eye coordination are a must if he is to keep the moving dot on the surface. Eventually, all the contours are traced. Map symbols are put in, and the manuscript is finished. It is an accurate representation of the area to be mapped, but the final map is still far from finished. The compiler's job has been done. Now, the draftsman takes over. The manuscript is copied photographically. Then it will be reduced to the exact scale ordered by the planners. Several copies of the manuscript are made on photosensitive sheets known as scribe coats and peel coats. The draftsman worked from these sheets and put in all the proper symbols and printed information. At one time, this was done with pen and ink. Now it's almost always done by a technique called scribing. The scribe sheet he works on is a dimensionally stable plastic-based material covered with an opaque coating. The cartographic technician transfers the manuscript information to the scribing sheet by cutting away the opaque coating. This leaves what is, in effect, a negative stencil of the manuscript. He has a number of scribing instruments with related points or blades specially designed for certain kinds of lines. But no matter which is used, the line must be clearly scribed with no residue or jagged edges. The cartographic technician must use extreme care and caution in placing symbols on the sheet, remembering that the final map will be printed in several colors and must be clearly understood to be useful. There are guidelines for him to follow in military publications. One or more sheets may be prepared for each color that will appear on the final map, usually black, red, blue, brown, and green. Some sheets requiring large blocks of color may be scribed in peel coat sheets. Peel coat sheets have thinner coatings that, when cut, pull away in sections, ideal for showing areas of vegetation, bodies of water, and so forth. Positioning of type for identification purposes is also the cartographic technician's job. He positions the type on separate named sheets, depending on the color desired. Each sheet must be in perfect register with the other scribe and peel coat sheets. When the cartographic technician's job is finished, there will be a number of different sheets for any given map, several for each color. Each sheet is checked for defects and registration. Some are in negative form, the scribe and peel coats, for example. Others, such as the names sheets, are in positive form. Positive sheets must be photographed to have negatives made of them before color proofs and final printing can be done. On a typical map, all these sheets may be necessary for printing in black. These may be necessary to print red. These to print brown. These blue. This for green. The number of individual sheets will vary from map to map. The final map begins to come to life in the color proof process. Negatives to be printed in a single color are exposed in sequence on a sheet of white plastic with a coating that's sensitive to that particular color. After developing, the first color is reproduced just as it will be printed on the map. Now the sheet is given a coating that's sensitive to another color, in this instance, red. The red negatives are exposed one at a time, developed and washed, and the areas to be printed red stay on the sheet. The same procedure is repeated with the other colors. Finally, the proof sheet is completed. It contains all the details in the correct map colors. This proof sheet is carefully studied by map editors, looking for errors, for names that cover up features, for problems in registration, for spots or pinholes in the solid tones, and so forth. Corrections are made and a second proof is made, and given this same kind of detailed inspection. When everyone is certain the map is correct and is clearly readable, it's ready for the final step in the map-making process, reproduction. Most military maps are reproduced by the offset photolithographic process. Offset presses are capable of high-quality work with long, high-speed press runs. Offset printing is done with flexible plates that are photosensitive. The images used to make the final color map are actually transferred to the plates photographically. The negative is placed against a photosensitive plate and then exposed to light. Each exposure is referred to as a burn because light shining through the transparent sections of the negative, in effect, burns an image on the plate. When there are several negatives for one color, multiple burns are used. Thus, everything that is to be printed in black is burned onto one plate. And the same applies to each of the other colors. Once the plate has been burned, it must be developed, just as a photograph would be. The result is a positive image of everything that will be printed in a given color. The image areas will attract ink and repel water. The non-printing area is receptive to water and will repel ink. This is the key to the offset printing process. There is one plate for each color, ready for the press. In most offset printing, each color is run one at a time. More elaborate equipment is available that can print several colors at a time, but most of the maps you will help make will be printed on a single color press. The first color printed is always black. After the black is run, the operator will wash up the press, change plates, and re-ink. He will do this step by step until all the colors are printed. In the offset process, the printing plate turns counterclockwise. It is dampened by a water roller to prepare it for printing. The water dampens the non-printing area of the plate, so it will repel ink. The image area repels water and remains receptive to ink. So when the plate passes the ink rollers, only the image accepts the ink. The inked image is then transferred from the printing plate to a rubber blanket that turns clockwise, leaving an image that is in reverse form. The rubber blanket actually prints the image, once again positive, on the paper. Printing from plate to blanket to paper gives the offset process great versatility, making it possible to print on a wide variety of papers, to get very fine detail, and to get very close registration of the various colors. When all 5 colors are run, the map maker can see the results of his work, a detailed topographic map ready for distribution to those that requested it, those that need it. There's another very important job performed by the map maker: revisions to existing maps. Maps must be updated periodically to include features that were not present when the earlier map making was done. To do this, the map maker must have a means of determining the true position of those features relative to the controls on the existing map. The map maker may have vertical aerial photographs to work from, or he may have to use oblique photography where displacement is a major consideration. Revision can be done on a device called a vertical sketchmaster. It permits an aerial photograph to be superimposed over a completed manuscript. The image size can be changed, and displacement in the photograph can be compensated for simply by adjusting the legs. When all the control points on the photograph fall into position on the manuscript, the compiler can trace off the features and details he wants. Another device used to transfer detail from a photograph or map is called a mirror stereoscope. It's a big help in map revision. Revised maps are handled just as new maps, following the same route through compiling, describing, and reproduction. To the soldier in the field, the new map gives the information he must know to carry out his mission successfully. To the military planner, a map provides knowledge that is vital to his decision-making. To countless others in non-military professions, it provides information that helps plan new roads, dams, airfields, flood control projects, any number of endeavors that help a nation progress and grow, both here and abroad. As a military mapmaker, you are part of an exciting and worthwhile field. You are helping your own country in the pursuit of peace, and you may be called upon to help other people in other places in their own development. There is much work to be done. Only a fraction of the Earth's surface has been accurately mapped. You will play an important role in completing the job.